Hello everyone, welcome on our YouTube channel. My name is Daljit Kaur, and on behalf of Physics Made Easy Kota, I'm going to discuss some important topics regarding chapter magnetism and matter. In this video, we are going to learn about the different types of the magnetic material, magnetic flux, Gauss law, magnetism and the magnetic intensity. So Faraday divides the magnetic materials into three different classes according to their magnetic behavior. The first one is the diamagnetic materials. Whenever there is the applied magnetic field, these materials get weakly magnetized but in a direction opposite to the direction of applied magnetic field. So we can say that a diamagnetic material is repelled by a magnet. For example, gold, silver, and many others are given in the slide. Then the second category is the paramagnetic material. These materials get weakly magnetized in the direction of the applied magnetic field. So we can say that they are attracted fably via magnet. For example, aluminium, calcium, sodium, and many others are shown in this picture. The next category is a ferromagnetic materials. Yes, these are those materials which get strongly magnetized in the direction of magnetic field. The best example, iron. They get strongly magnetized. They get easily attracted, easily magnetized. Another example like steel, nickel, and the ferromagnetic effect is noticed even in the presence of a weak magnetic field. With a rise in temperature, it becomes less easier to magnetize the ferromagnetic substances, but it can easily detected in the presence of the weak magnetic field. Also, ferromagnetic materials are further categorized into two types. First one is a hard ferromagnetic material, and the second one is a soft ferromagnetic material. The first category of the ferromagnetic material are hard ferromagnetic materials. These are those materials which are not magnetized easily. In a ferromagnetic material, magnetism remains even when the external magnetic field to magnetize it is removed. A hard ferromagnetic material is used to make permanent magnet. Example, lodestone. A compass needle is formed from hard ferromagnetic material. As the name suggested, soft ferromagnetic materials are those which is demagnetized easily. So a soft ferromagnetic material is demagnetized as soon as the external magnetic field is removed. For example, iron. These are used in various purposes to make the cores of transformers, electromagnets, magnetic tapes and computer disks. So why the diamagnetic material behave in such a manner? It could be explained only from its electron theory. So in a diamagnetic materials, electrons in an atom are assumed or considered to be exist in pair, and these electrons move with equal velocities but in opposite direction. And in the absence of the external electric field, the magnetic moment of both the electrons are equal but opposite in direction. So we can say that the net magnetic moment of each electron of diamagnetic substance in absence of magnetic field is taken as 0. So now we are going to understand the behavior of the electrons in the presence of the uniform magnetic field. So let there be a uniform magnetic field that is applied perpendicular to the plane of rotation of electrons and in the downward direction. As this picture represents the magnetic field which act in the downward direction, and we can observe that there are the two forces. One is a centripetal force, and besides centripetal force an additional magnetic force act on each electron, and this force is directed away from centripetal force acting on one electron revolving anti-clockwise, and it act towards the centripetal force acting on the electron revolving clockwise. Thus, velocity of electron revolving anti-clockwise decreases and the velocity of electron revolving clockwise increases. Therefore, magnetic movement of electron moving with velocity v1 as in the picture decreases, and the magnetic movement of electron moving with velocity v2 as shown in the picture get increases. We calculate the net magnetic movement of an atom, and we observe that the direction of this net or the induced magnetic movement is perpendicular to the plane of rotation of electron and upward. So induced magnetic movement is directed in a direction opposite to the direction of the applied magnetic field, which was in the downward. So we can say that when the induced magnetic movement of all atoms get added, and the diamagnetic substance has induced magnetic movement in the direction opposite to the direction of applied magnetic field. So this is the reason why diamagnetic substances get weakly magnetized in the direction opposite to the direction of applied magnetic field. It is very difficult to magnetize a diamagnetic material. They require very strong magnetic field to show magnetic properties. Their magnetic behavior normally does not depend upon change in temperature. Now we are going to understand about the electron theory of the paramagnetic materials. For the paramagnetic materials, in the absence of the magnetic field at a thermal energy and at the presence of the room temperature, the atomic dipoles are oriented in random fashion and cancel the magnetic moment of each other, and thus the net magnetism of a material is zero. Also, it is noted that the electrons of atoms are considered to have two motions. One is the orbital motion, second one is a spin motion around their axis, and the vector sum of these motions decide the net magnetic dipole moment. Each atom of paramagnetic material has some permanent magnetic dipole moment. The A part of this picture represents the condition when the net magnetism of a material is zero and the dipoles are oriented in the random fashion. When we applied a magnetic field to the sample of the paramagnetic material, the atomic dipoles tried to align themselves in the direction of the field as shown in the figure B. But at room temperature, the sample fails to attain complete alignment due to thermal energy, so the sample get weakly magnetized in the direction of applied magnetic field. This weak form of magnetism is called paramagnetism, and the paramagnetic material loses magnetism with a rise in temperature. Now we are going to talk about the electron theory, which is also known as the domain theory of the ferromagnetism. You can easily look in the given picture in the figure A. Each atom of a ferromagnetic substance has a permanent dipole moment due to unpaired electrons in the outer shell. The interaction between different atoms in the neighborhood is called exchange interaction. This interaction is very strong to align the atoms with their magnetic movements in the same direction over a small region, which is called as a domain. And this domain having a very small volume. The arrow in each domain represent the net magnetic dipole moment of the domain. The magnetic dipole moment of all domains are randomly oriented. Hence, the net magnetic dipole of the ferromagnetic substance is zero in the absence of external magnetic field. But look at a figure B. This figure represents a ferromagnetic substance in the presence of external magnetic field. So in this case, the magnetic dipole moment of each domain align itself in the direction of applied magnetic field. In other words, we say that the size of the domain having dipole moment in the direction of applied field increases, and the size of domain having dipole moment in the direction other than the applied magnetic field decreases. At low external magnetic field, the alignment of magnetic dipole moment in the direction of applied magnetic field is partial. However, when the applied magnetic field keep on increases and it increase to a high value, the alignment of magnetic dipole moment is perfectly in the direction of applied magnetic field as shown in the figure B. Thus, a ferromagnetic substance is strongly magnetized in the direction of applied magnetic field. Consider a surface capital S in a uniform magnetic field. Let the surface is made up of small elements each of area vector dA vector. If the magnetic field, that is B vector, makes an angle theta with the area vector, then the magnetic flux linked with the small element is given by the expression BA cos theta. So what is a magnetic flux? Magnetic flux are the number of magnetic field lines passing through a given surface. Yes, there is a Gauss law in magnetism, but this time this law we are going to study in the case of the magnetism. And according to the Gauss law in magnetism, it states that magnetic flux through any closed surface is zero. This law suggests that an isolated magnetic poles cannot exist. These isolated magnetic poles are also known as a monopole. So this suggests that monopoles cannot exist. This law also explains that magnetic field do not begin or end at any point. That is, the number of lines entering a surface equals the number of lines leaving the surface. There is no source or sink. Here are few terms which we must understand in order to understand the magnetism and the effect of the magnetism. The first term is the magnetization. Magnetization is the degree or extent to which a substance is magnetized when placed in a magnetic field. The next term is the intensity of magnetizing field, which is indicated by a symbol capital H. It represents the degree to which a magnetic field can magnetize a material, and it is also known by another name like magnetic intensity, magnetizing force, or magnetic field. It has some another definition in terms of a solenoid, that is a number of amperes turn per unit length of a solenoid required to produce a given magnetizing field. It is measured as ampere per meter. That is the unit of the dipole moment divided by the unit of volume. Next term is a magnetic permeability. It is denoted by the symbol mu. It represents the nature of a material, that it is describing the property of the material, that the extent to which the magnetic field lines can enter a substance, or we can say that up to which degree a magnetic field can penetrate a given substance. Mathematically, it is equal to the ratio of the magnetic field inside a material to the applied magnetic field intensity. Magnetic susceptibility represents the property of the substance, which shows how easily a substance can be magnetized when placed in a magnetizing field. It is also defined as the ratio of the intensity of magnetic magnetization to the intensity of magnetic field, or we can say that strength of the magnetic field. Magnetic permeability and magnetic susceptibility has a relation between them, that is mu r is equal to 1 plus xi m. So now it's time to check your knowledge. Here are few questions. Go through each question and try to answer these questions. Now on this page there are the questions from the question number 6 to question number 10. Answer these questions from your knowledge what you gained in this video lecture. Thank you for watching our video lecture.